Good evening, one and all present here.
Good
I
evening.
request YouTube coordinators to start the live.
Yeah, we are live.
Myself, Nitya Parekh, your host for today's session and a part of Team International Colloquium on Emerging Technologies 2021. Neil Armstrong once said, "That's one small step for man, one giant leap for mankind." Today is the day we all were waiting for. Yes, today we are lucky enough to have a look at the world's most advanced technological institution, NASA's Clouds and Earth's Radiant Energy System. We will have today Dr. Mohan Shankar sir and Dr. Anum Ashraf ma'am describing NASA's Clouds and Earth's Radiant Energy System and various aspects pertaining to it. Now, I would like to invite Dr. Rashesh Mehta sir, Head of Electrical Engineering Department, to introduce the speakers of today's session.
Yes. Good evening, all the participants and the IEEE student grant team. Good morning to both the speakers of today's session. So I would like to introduce Dr. Mohan Shankar first. Dr. Mohan Shankar is a research scientist at NASA Langley Research Center. He has worked as senior research scientist at Science Systems and Applications in Hampton, USA. He has completed his master's MS in Electrical and Computer Engineering in Optical Imaging Systems from Duke University. He has a US patent registered to his name on the topic of sensor system for identifying and tracking movements of multiple sources. His specialties include broadband radiometry and radiometric calibration, optical design, calibration and testing of infrared and visible imaging system modeling. So he will be delivering the talk on clouds and Earth's radiant energy systems, CERES. So welcome, Dr. Mohan Shankar. Uh, the next speaker in the same session is Dr. Anum Ashraf, who is a principal investigator of Demeter IIP at NASA. She has worked as a lead research associate at the Air Force Institute of Technology for over 2 years. She holds Doctor of Philosophy in Mechanical Engineering from Virginia Tech and has completed her master's degree in Optical Science and Engineering from US Air Force Institute of Technology. She has been awarded Early Career Achievement Medal in 2015 at NASA Agency Honor Awards for exceptional achievement in radiometry, optical and calibration design for Earth radiation budget, remote sensing programs. She has also been awarded NASA Group Achievement Award Clouds and the Earth Radiant Energy System Series in October 2014 at NASA Honor Awards. She will be delivering the topic of Clouds and Earth's Radiant Energy System Series today. So I welcome to both the speakers.
Thank you so much, sir, for your kind introduction. Just a little note before we get started. If you have any questions during the session, please type them in the chat box. They will be conveyed to the experts by our moderators during the Q&A session, and a feedback form will be circulated anytime between the session, which will be active only for 15 to 20 minutes, and filling this feedback form will be counted as your attendance. Also, do note that the participation certificate will be given only to those who have attended at least 4 sessions of ICET 2021. Hold your seatbelts tight, it is going to be a great session. Now, I would request our honorable experts to carry on with the session. The stage is all yours.
Thank you very much for that kind introduction. Good evening, everyone. My name is Dr. Mohan Shankar. My colleague, Dr. Anum Ashraf, and I are both members of the Climate Science branch of the Science Directorate here at NASA Langley Research Center in Hampton, Virginia. Thank you for inviting us to give us a talk at ICET 2021. It'll be our pleasure to talk to you about Earth radiation budget and the measurements made by CERES and the follow-on instrument Demeter. We'll both be talking about Earth radiation budget. I will lead it off with providing a background and then talk about the CERES project and the CERES instrument, while Dr. Ashraf will provide a brief overview about the next generation instrument currently under development here at NASA Langley as a part of a NASA instrument incubator program called Demeter. The title of the talk is Measurements of the Earth's Radiation Budget, Climate Data Record by CERES and Demeter. I thought I'd start off by introducing myself a little. You might have heard already a brief introduction of myself, so I thank you for that. But my role currently on CERES is I am the deputy project scientist. And what that really means is I am responsible for developing and implementing calibration and validation protocols to ensure timely availability of CERES data products. And another piece of my responsibility includes monitoring the health, safety, and coordinate the operations of all the CERES instruments that we have today. You already heard about my educational background, so I'm going to skip over that for now. So this is the outline of the talk. I'll start off by introducing the concept of the Earth radiation budget and what it means, the implications. I'll briefly talk about the history of Earth radiation budget instruments and the measurements made throughout the years. And then I'll get into a little bit more detail about the CERES project, what science it accomplishes, the instrument, the measurement process, briefly talk about the calibration and the validation, what kind of data products, and then sort of end with some significant recent results that were published by the CERES team. And then transition over to the continuity of these measurements, which Dr. Ashraf will then take it over from there to talk about the Demeter project. So we'll start off with the Earth's energy budget and its implications. This is a schematic showing the Earth's energy budget. So essentially, this is a control volume, if you want to think about it. Where we have the top of the atmosphere, represented here by this dotted line. And then you have the Earth's atmosphere, and then the surface, in this case, is just the ocean. And so the various components of the energy budget that we consider are, we have the source of the sun, being the sun, and that, provides incoming solar radiation to the Earth. And then some of this energy is reflected by clouds, some of that is reflected by the atmosphere, some of that reflected by the surface. All of this combined, we get a component called the reflected solar radiation. And then this absorbed component ends up heating up the surface. And so you'll have, thermal radiation from the surface itself that starts emitting from the surface, some of which is also, absorbed by components in the atmosphere, which in turn emit upward and downward. And so you'll have thermal energy that's absorbed at the surface. And what leaves the Earth is what we call the outgoing thermal radiation or long wave radiation. So when we talk about energy budget, what do we really mean? We're trying to calculate the imbalance, the net imbalance, which is the difference between the energy that's entering the Earth and the energy leaving the Earth. So you have incoming solar radiation and these two components, the reflected solar and the outgoing thermal leaving the Earth. The difference between this and the sum of these two is what we're trying to make measurements of. And I'll get into why these are important. So why is the Earth's energy budget important? These have economic and political implications. The data that we provide are critical for making informed environmental and economic policy decisions which influence current and future generations. And we also provide data to help improve prediction models. And by prediction models, I mean either climate models or weather models, which essentially are trying to track the natural internal variability of the Earth system. And in order to do that, we need accurate and precise observations over extremely long time scales, because the Earth itself has some internal variability, and instruments that we launch to space have their own artifacts and noise sources. And in order to decouple what's coming from the Earth, we need measurements over really long timescales. And that's what these observations enable. The next aspect is human-made climate change, or what we call anthropogenic climate change. which is a perturbation of the energy balance of the Earth caused by changes in the atmospheric concentrations of greenhouse gases and aerosols. And so in order to monitor the changes caused by these increases in atmospheric concentrations of greenhouse gases and aerosols, we need accurate and precise observations of the energy budget. So in response to a increase in the TOA radiation imbalance, the Earth's energy flows are altered as the system adjusts to a new temperature. And we also have feedbacks in the system, which occur due to water vapor, the clouds, atmospheric lapse rate, which is essentially the change in temperature as you go higher up in the atmosphere, and then snow and ice. All of these components act to counter or enhance the change in the temperature. So all of these components are variable, and in order to be able to accurately measure them, we need to be able to make these measurements over long time periods and also make them accurately. So how does the Earth respond to a perturbation? So if you consider this schematic here or a picture here of the Earth, you might have forces acting on the system, and these are forcings that include natural forcings, which are the sun, changes to the input, or the changes happening in the sun, Earth-based natural causes like volcanic eruptions, and man-made changes, which include increases in concentrations of carbon dioxide or other greenhouse gases, aerosols, changes in land cover as more development happens on Earth, etc. Then the Earth system has a response to this input, as well as having some feedback. And that feedback includes things like the changes in water vapor, the temperature or lapse rate, as I talked about, surface albedo in clouds, etc. And so as the system responds, humans have to face the impacts or have to deal with the impacts as a result of the Earth system responding. So next, I'm just going to again explore or dig into a little bit of detail about the Earth energy budget and surface temperature and how one impacts the other. So this is a simple schematic which shows the atmosphere. You have an ocean, and then and T sub S here represents the temperature of the surface of the ocean. And so you have two components. One is the absorbed solar radiation, which essentially acts as an input to the system. And this absorbed solar radiation is incoming solar radiation minus the reflected solar radiation. So that's what's retained and absorbed. And then as the system absorbs this, as the components in the atmosphere absorb the solar radiation, they emit, they heat up and they emit, and you have energy leaving the system called the OLR, or the outgoing long wave radiation. So the difference between these two is the net, what we call the net TOA. TOA is the top of the atmosphere radiation. And so if you have a situation where, in an ideal circumstance where you have no external forcing, where there is no change in the system, where either being natural or human made, when there's no forcing, the temperature of the system will so adjust that the outgoing long wave radiation will match the absorbed solar radiation, and therefore the net is zero. This is an idealistic situation. This is not what represents current reality, but this is what would happen if you had such an ideal situation. So therefore, if this TS will actually equilibrate at a certain temperature, and if you take long-term trends with time and average them, that T sub S will actually stay constant. There is going to be very little change with time. Now, in a more realistic situation where you do have increases in atmospheric greenhouse gases, things like carbon dioxide and methane, what happens is the net actually increases. It's going to be a net positive. And this is because greenhouse gases trap thermal radiation that's leaving from the surface, which reduces the amount of energy leaving the Earth and ends up heating up the Earth. And again, what happens is 90% of this excess heat actually gets stored in the ocean, and the rest of it actually warms the atmosphere, land, and melts in the snow and ice. And so if you take this T sub S over a long period of time and average it, it actually shows an increase. There is a caveat to this. At timescales of up to a few decades, there are natural variations, fluctuations of this of the surface temperature. That's resulting because of fluctuations in ocean currents and atmospheric wind patterns, and that could result in temporary offsets to or increases or augmenting the increases in the surface temperature associated with global warming. So we have to be a little careful in just looking at the surface temperature over long periods of time to claim that there is actual warming going on, because there are these effects that temporarily cause an increase or decrease in the surface temperature. These all get flushed out when you look at really long-term trends. That's when all of these variabilities actually fall out. So next we'll talk about what are the symptoms if there is a positive energy imbalance or the net top of atmosphere radiation is greater than zero. This leads to all sorts of things that we all are quite familiar with. It causes a rise in the Earth's surface temperature, atmospheric moisture, global mean sea level, melting of ice shelves, etc. It shifts atmospheric circulation patterns, and it causes extreme weather, more occurrences of extreme weather events, and these are floods, droughts, forest fires, you name it. And it's all in the news more recently, the increase in the in occurrences of these weather events. It increases the ocean heat content because most of the energy is actually stored, extra energy stored in the ocean. It leads to ocean acidification, impacting fish and other marine life. And it also decreases the sea ice, and that's related to the increase in the global mean sea level as well. And you have impacts to glaciers and all such effects are that you see nowadays. So now this net top of the atmosphere radiation, if you take a look at it now from the Earth, if you take a look at it as a function of the latitude on Earth, it's not a constant. You don't have an equal distribution. It turns out that at the higher latitudes, which are represented, so this x-axis here is a sign of the latitude. So these correspond to the higher latitudes, and the 0 corresponds to the equator and tropical regions around here. So you have a net deficit in the higher latitudes, and then you have a net surplus in the lower latitudes near and mid latitudes as well. So there is this distribution now spatially, and so if you want to get a measure of what is happening on the Earth, it requires not only observing over long time scales, we also have to observe this over spatial scales, or in the amount of ice in those regions. And there is a direct implication of an increase in the, just a visual to sort of confirm what we think must be going on. Talking about the history of Earth's radiation budget measurements. Now, I've given hopefully a good overview of why what are Earth's radiation budget measurements, why they're important. Now we'll move on to how it's been done over the years. The first Earth radiation budget mission was on the Explorer 7, which was launched in October of 1959, And this is just a cartoon showing the Explorer 7. The Explorer 7 carried what was this instrument here called the Radiation and Heat Balance Detector, which actually made the first crude measurements of the ERB. And Dr. Werner Sumi, he designed this instrument, and which really initiated the era of satellite climate. And he is regarded for his not only this, for many other contributions as well, as the father of satellite meteorology. So a little bit more about this instrument. It black. The black pair would absorb sunlight, both directly coming from the sun and that reflected from the Earth. And then also it would absorb the Earth emitted radiation. The white balls or hemispheres would would reflect sunlight, but all would collect or absorb the Earth emitted radiation. So using this data, researchers were able to calculate the amount of sunlight and the Earth emitted radiation from the temperature. Essentially, first of those crude set of measurements. Instruments were then designed to make better measurements of the Earth's radiation budget. The next one is the model. Then we had two CERES instruments, flight models 1 and 2, which were on the Terra spacecraft, which was launched in 1999. Aqua spacecraft launched in 2002, which carried two CERES instruments, flight models 3 and 4. The SUMI and PP spacecraft launched in 2011, which then carried only one instrument, flight model 5. And NOAA 20 spacecraft launched in 2017 carried also one instrument, the flight model 6. All of these instruments were identical in design, and the design was conducted back in the 80s and early 90s, with the first launch in, as I said, 97. But the most recent instrument actually still carried the same design and components that were built back then, which were available for use and launch, and they were qualified for launch. Barring the instrument on the TRIM mission, all the instruments aboard Terra, Aqua, SUMI, and PP, and NOAA 20 are still currently operational. So you see instruments that were originally designed for something like 5 or 6 years have way outlasted their design lifetime, and we're in the 21st year of operations of instruments on Terra, and similarly for Aqua as well. So these are remarkable instruments, and they've performed exceptionally well. And so this is a schematic of the CERES instrument, and I'll talk a little bit more about this in a few slides. So just to give a comparison, the first instrument was on an Explorer, which is a picture of it is shown here, and a person standing here to give you a sense of scale. This instrument was in orbit, and it would spin around its axis to make those measurements. And we've moved on from this to something like this, which is now what we can consider as an Earth observing system, because we carry multiple instruments that enable the data records that we are producing, and also all the amazing science that it enables. The CERES instruments are shown here, and you'd see all of these other instruments are bagged up, which this is ready to be integrated onto the launch vehicle. So next, we'll get into what I was originally going to be talking about, the CERES instrument or the CERES project. The CERES stands for the Clouds and Earth's Radiant Energy System. And we'll start off talking about the science goals. The goals are to produce a long-term integrated global climate data record of the Earth's radiation budget. And we do this at the top of the atmosphere from the surface, and then we also produce the associated cloud, aerosol, and surface properties as well. This also enables improved understanding of the variability in the Earth's radiation budget. We also need to understand how it changes with time. And we also produce data products for improving climate models and evaluating them as well. So a lot of the data products that we produce are provided to the climate scientists who feed these as inputs to their models to validate what they're predicting and also improve their models moving forward. We have several scientists on the CERES team and scientists and other researchers who have contributed to this IPCC reports over the years, and they've actually used CERES data to demonstrate what has happened and what we should be looking for in the future. Again, just to elaborate a little bit more, CERES observations provide critical data for quantifying how the heat uptake of the planet, which means how much energy is being absorbed by the planet, changes on different timescales, starting from monthly out to decadal type timescales. It also provides data to constrain climate model projections of future warming by reducing the uncertainty in the cloud feedback. So clouds are a big source of uncertainty in trying to understand how clouds impact all these various components. And so cloud feedback is something that CERES data actually provides useful data for. It also helps in quantifying the aerosol radiative forcing, and to elaborate, just as I said, understanding cloud processes and the feedback as well. So these are sample plots from a given month from CERES data. We get things like the planetary albedo of the globe for a given month. And this is what the emitted thermal radiation is. If you take the if you look at the net top of the atmosphere radiation, this is what it looked like for one given month. This is just to give a sample of what it looks like. So back to the Earth's energy budget schematic and where CERES fits in. So what I've done here is included actual numbers here for the various components. And I'm not going to go into all of the details here, but if you just look at the magnitude of these numbers here, they're fairly large. If you look at the top of the atmosphere imbalance, the energy imbalance, this is a pretty small number. And we want to track changes in this number with time. And so this requires really precise measurements over really long timescales, which is what CERES enables. The incoming solar radiation are measured by an instrument called TSIS, which is the total and spectral solar irradiance sensor. And as we have already talked about, CERES makes measurements of the reflected solar component and the outgoing thermal radiation. The numbers in parentheses here are the uncertainties of this number at a 1 sigma level. Here, next, this is just another example of a data product produced by CERES. This shows the reflected solar energy, which sort of looks like the albedo or albedo, which is essentially the brightness of the Earth at any given time. This is essentially computed from the reflected solar energy, and we have outgoing long wave or thermal energy for a given month here. And so we produce these data that you can create hourly maps, and we generate these on 1 degree latitude, longitude grids to get these top of the atmosphere, and also generate the top of the atmosphere to surface all the components in between. And we generate all the many other data products at various temporal and spatial scales as well. This is a picture of a launch of the Suomi and PP spacecraft. This was on a Delta II rocket back in October 2011. This was launched from Vandenberg Air Force Base, now called Space Force Base in California. And the whole spacecraft is carried in this in the nose area of this rocket. And in there, this is just an artist's description of an artist's drawing of the SUMI and PP spacecraft, which carries the Ceres Flight Model 5 instrument shown here. In addition to Ceres, we have 4 other instruments. One is a microwave sounder called ATMS, Advanced Technology Microwave Sounder. We have the CRIS instrument, which is a cross-track infrared sounder, OMPS, which is an ozone mapping and profiler suite, and Weir's visible infrared imaging radiometer suite, and of course the Ceres instrument as well. A little bit of detail on the Ceres instrument itself. As I mentioned earlier, Ceres measures the reflected solar radiation and the outgoing thermal radiation. And in order to be able to make measurements of these components, we have to span a really large wavelength range, starting from the visible out to far infrared. So this instrument is unique in that it makes really broad band measurements. The instrument was designed, built, and tested by Northrop Grumman Aerospace Systems in Redondo Beach, California. Ceres instrument has 3 sensor assemblies. Each of them are essentially Cassegrain telescopes with bolometer detectors. These are co-aligned and mounted on a spindle, which rotates about this elevation axis. So it actually scans the Earth as it moves along the orbital track, back and forth as it makes measurements of the Earth. It can also be rotated in the azimuth plane, so it can be rotated this way as well, if you can see my cursor. And the measurement channels are, we have a shortwave sensor that goes from 0.3 to 5 microns. A total sensor that really measures all energy, because there is no filter to block out any or reflect any energy. And then we have 2 variants of this third channel. The flight models 1 through 5 carried what we call an atmospheric window channel, which measured just the 8 to 12 micron band. And then the flight model 6 instrument carried a long wave sensor that measured the 5 to 35 micron band. So just the true long wave. The measurement accuracy goals were 0.5% for long wave and 1% for short wave, 1 sigma. Very demanding measurement requirements. And a little bit more details on the instrument. It's roughly about 45 kilograms. Data rate is really low because we make, essentially integrated across all these wavelengths measurements of energy, and we downlink those the time series of these measurements. So we have 10 kilobits per second type of data rate. The size of this instrument is about 2 feet by 2 feet by about 2.5 feet. And the design life, as I said earlier, is something like 6 years. But as I've already mentioned, we have instruments that are running into their 21st year. So they've been extremely robust and give really high quality measurements. Now, this is just a graphic and hopefully a video that shows the orbital planes in which these various Ceres instruments are flying. So you have Terra, Aqua, SUMI and PP, and NOAA 20. They're in slightly different orbits. Not only are they in slightly different altitudes, but they also have different orientations as well. So they are all polar orbiting satellites, and so therefore they fly over the poles as the Earth rotates under. Terra has a 10:30 a.m. nominal local equatorial crossing time. So if you look closely enough, you'll see that the Terra instrument will cross the equator at around 10:30 a.m. local time, wherever it crosses on the Earth. The other 3 spacecraft have an afternoon, a 1:30 p.m. nominal local equatorial crossing time. And there are implications to the measurement itself about why these 2 different times are significant. and that it has to do with the morning, the measuring the effects in the morning versus the afternoon, and the changes in clouds between the morning and the afternoon. Um, the next video here shows how you obtain global coverage from a single spacecraft. And so, as I mentioned, the CERES instrument scans back and forth, and it actually scans perpendicular to the orbital track. So if the spacecraft is moving in an orbital track this way, it scans back and forth, and the Earth actually rotates under it. And so you have multiple orbits, and something like 16 orbits in a given day, you actually span the entire globe. And I'll talk about the implications of that in the next couple of slides. This is just to give you a visual representation of how measurements are made. So the spectral, now we want to talk about what type of measurements we make. We need to understand what are the sources, or trying to understand what type of energy we actually get from the sun and the earth. This graphic here just shows a representation of the solar spectrum and the earth emitted spectrum. And so you see, the sun, has a brightness temperature from which we can get a spectral radiance curve. And we've scaled it just to get it into the same scale as the emitted component. But you see that the reflected and the earth emitted components are actually separated from each other. So it enables us to measure these independently. So to go in a little further, essentially you start from the UV out to the shortwave infrared, and then you have the thermal components in the infrared. And you have, in addition to this, various components in the Earth's atmosphere. You have water vapor, carbon dioxide, oxygen, etc., which have their own spectral signatures. They have their own absorption features and such. And so this plot here just shows a representation of if you combine all of these components, this is what it would look like. And this blue curve represents what the outgoing thermal radiation is. So we need to be able to measure this, and that's what CERES enables. And the downgoing solar radiation that's leaving the Earth after being passing through the atmosphere has a structure like this, which essentially looks like the solar spectrum, but you have these absorption features. These are the type of measurements we make. And in order to make those measurements, we have a really broad band sensor, which covers, this is in a log scale from 100. As I mentioned, the three channels that we have, you have a shortwave channel, which is shown in blue, the total channel in red, and the yellow is the atmospheric window channel. So we have these broad spectral channels. We integrate over the entire spectrum to get these different components. We don't care about the what's in each wavelength band, but we integrate across all of them. I'm going to cover this really quickly. This is a science traceability matrix, which really maps science needs to measurement characteristics. So these represent science questions we are trying to answer, then what strategy we use, and what instrument measurements enable answering those science questions. Essentially, we're trying to provide a top of the atmosphere radiative flux of the reflected solar and the outgoing long wave components at a 1 by 1 degree latitude longitude grid box on the Earth every hour. And this is where the complexity lies. CERES provides these observations at about 25 kilometers, which represents the field of view of the CERES sensor. But because of the scanning process, we get global coverage, and we can get data products at these different temporal and spatial scales. We also need to get cloud properties, and that's enabled using the MODIS or VIIRS instrument that is on board the same spacecraft. And since CERES instruments, as you saw in that video, every point on the Earth every hour, in order to generate hourly products, we actually use geostationary observations. And we combine those with the CERES observations to provide these temporal and spatial scales that CERES enables. We also use ancillary data sets like the solar irradiance and some other data products to inject them into our stream, and then provide all the data products that the science community uses today. So the challenges with ERB measurements, that we need to make these measurements at or provide observations at or provide fluxes at these 1 degree by 1 degree latitude longitude resolution grids. And as I mentioned, series instruments do not and cannot sample the entire globe on a continuous basis. ERB sensors are typically undersampling in all dimensions, in time, space, in spectrum, as well as in angular coverage, which creates a unique and a complex systems engineering problem. So how do you try to get these observations at this spatial scale and those time scales to address all the science goals, and how we address this is by a high level of data fusion. We infuse data from all multiple data streams in order to provide these accurate, top of the atmosphere fluxes. And this just goes into a little bit more detail. A given orbit, if you take a sun-synchronous satellite over a 24-hour ground track, these are the different ground tracks as the day goes by, as 24 hours go by. As you can see, the polar regions are sampled every 90 minutes. That's the orbital period of any of these sun-synchronous satellites. And the equatorial regions, however, are undersampled. So you see a large gap between these observations. We need to make these samples at these 1 by 1 degree grids. The question really is, how do we fill in these observations? And we use geostationary satellites. So these are geostationary satellites carry these imagers that are orbiting the Earth at around 36,000 kilometers, and they view the same portion of the Earth throughout. And so there are multiple of the geostationary satellites, and these are sort of the sub-satellite points. So this is what it is centered on the globe, if you were to project it. So you can see it actually provides fairly good global coverage. Doesn't do so well in the polar regions, but the geostationary imagers they measure in narrow spectral bands. We measure broadband, and these are not optimized for the type of measurements we're making. So we do a lot of processing of that data in order to get what we need. So just to throw it out there, we do a lot of data fusion. We have data coming in from geostationary satellites, and we have polar orbiting instruments, multiple of these. And this gives you a snapshot of the level of complexity of data fusion that's involved. Multiple instruments over multiple platforms. All of this are integrated to obtain climate accuracy and radiative fluxes from the top to the bottom of the atmosphere. The CERES scan, as I said, it goes back and forth. So when we have to look at the type of sampling it gets, we have to consider what the orbital altitude is, what type of range of angles we have to cover. And depending on the orbit, as you see here, different spacecraft have different orbits. We have to look at how to scan, at what rate to scan, and how depending on the altitude. So it's a optimization problem as well in that respect. The cross-track spacing, the spacing between individual footprints are driven by the rate at which we scan back and forth. And the spacing along the direction of the orbital track is given by how fast this spacecraft is moving and how fast we scan back and forth as well. We look at the different capabilities that CERES operates, and I'm not going to go into a lot of detail here as just in the interest of time. This is our typical nominal science mode where as the satellite moves, we have instrument making observations back and forth. So we get this nice sampling of the globe. And then we also have the ability to rotate in the azimuth axis as well. So we can get these nice patterns on the globe, and it provides increased angular sampling. And there are implications to calculating radiative fluxes from the measurements that we make from CERES, which are radiances. I'm not going to get into those details here, but That's where we use to develop models to enable that conversion. We also have the ability to target any specific part of the Earth. If you're looking at a specific point on Earth, we can scan back and forth by rotating both in elevation and azimuth, such that we sort of get an intersection of all these different scans on a specific point on Earth. And we also have tracking capability. If you want to lock on a specific target on Earth as the spacecraft moves, we adjust azimuth and elevation rates to be able to look at any point on Earth. Again, I'm just going to give a high-level description of calibration, because that's a whole talk by itself. In order to meet these demanding accuracy requirements, there is a calibration and validation protocol. And this involves pre-launch. Before launch, we need to characterize the instrument really well. And this is typically done in a simulated operational environment, which is typically a vacuum chamber. And calibration really is how well the instrument makes measurements with respect to a given standard, like a NIST standard, for example. It really gives a sense of how close the measurements are to the truth. And so you can have a measurement of a known truth and how close is your instrument making measurements of that truth. And so it gives you do that characterization on the ground. And then post-launch, we actually monitor any changes of the instrument with time by we have onboard calibration targets for monitoring any changes. And we also look at vicarious targets, by which I mean Earth targets like deserts or clouds or oceans. And we also look at celestial targets like the sun or the moon, and all giving bits and pieces of information about how the instrument actually performs. And this table here just summarizes it. I'm not going to go into any amount of detail. There are onboard targets. We have infrared targets, a reflected solar target, a solar diffuser, and then we use various Earth targets to get a sense for how instrument performs. Next, I just wanted to give a sense of what type of data products we produce. It's a very complicated data stream, as you'll see here, and I'm not going to get into any amount of detail. There are different levels as shown here, which really indicate different levels of processing, which includes infusion of different data streams and processing the data using that data from those different streams. The level 0, which is really the raw data, the native data that we get from CERES instruments, is shown right on the top there. And we have a stream of data just these instruments data. And then we have infusion of these different other input data streams, and we create all these different other data products at different time scales, spatial scales, etc. So that's just to show the level of complexity that is involved in generating all the data products. And all of these data products are available for public consumption. Now, what can we do with these data products? And here's an example showing, we can get these data products at temporal scales, spatial scales that we talked about. What can we do with it? Here's an example of the net flux for a given day. This is a example for 24 hours. As you can see, as the sun illuminates different parts of the globe, you can see the net increases only for those regions. And you can see the different parts of the Earth that are illuminated by the sun. And then for those that are not illuminated, you sort of have a negative net flux. So there is a deficit in those regions, and there's a net positive when the sun illuminates it. So it gives you the ability to look at all these different types of phenomena in different time scales, spatial scales, etc. Just to give an example there. Also, we can get similar data over really long time scales, and this shows data right from 99 out to 2019, I think, of incoming solar, reflected solar, absorbed solar, and then outgoing long wave and the net as well. And so you can get, since you're having data products at these different resolutions, you can observe changes with time of any geographical location or the Earth as a whole, and look at phenomena that are changing with time. And so highly reflective parts are things like any land component, anything on land is highly reflective. Deserts are particularly highly reflective. Clouds are highly reflective, like the desert here in Sahara. And then you can look at changes in trends of the net top of the atmosphere radiation, and if there are any influence, what are causing those changes in those net radiations. So it really gives you this tool to be able to monitor these changes with time. And one such example, if you just take the global mean of all of these all these different components, the absorbed solar radiation, the outgoing long wave, and the net, and these are taken using data from the various spacecraft. The Terra, Aqua, and NPP trended with time right from 2000 out to 2020. You can actually see how consistent all of these data sets, they all line up on top of each other. It shows how consistent all of these data sets are. This is the net. Anything that's positive is really absorbed. There's more energy absorbed in the system, in the Earth system, and negative is loss. So you track these changes with time, and it gives you a sense of what's happening globally over really long timescales. I'm going to sort of, this is the last part of my talk. This is a significant result, a more recent result that came out in geophysical research letters. Norman Loeb, he's the PI for the CERES project, wrote this paper titled "Satellite and Ocean Data Reveal Marked Increase in Earth's Heating Rate." This paper actually garnered a lot of attention in the media as well because of the claims made based on observations from CERES, which are the satellite observations here, and an independent measurement from in situ ocean measurements using the Argo network. And the Argo network are really a bunch of floats that are distributed all over the globe, as you see here. And they collect temperature and salinity profile and the trajectory for every 10 days. And these are uploaded to satellite and made available within 24 hours. So what you can now do is take measurements of the net top of the atmosphere radiation, and also look at what the energy that's absorbed in the ocean or the temperature changes in the ocean and compare those two. And that's exactly what they've done. And you can see over this period of time from mid-2005 to about mid-2019, you can see a very consistent trend with time. And that is remarkable because there are essentially two independent sets of measurements, very different types of measurements, and they show really good agreement. One thing you'll see here is this trend is not significant. I mean, if you look at the absolute numbers here, they're not that big, 0.5 plus or minus 0.47 watts per meter squared per decade. But to give a sense of perspective, one of the authors on that paper, Rick Johnson, had spoken to the Washington Post, and he said that this energy increase, which has been shown in this paper to double over this imbalance has doubled in this period of time, is equivalent to something like 4 detonations per second of the atomic bomb dropped on Hiroshima. Or another example he cited was, if every person on Earth uses 20 tea kettles at an instant, the amount of energy that we're because the area of the Earth is so large, it gives you a real awakening as to how much energy that really corresponds to. So this is one of those things that one of those science accomplishments that can be achieved by these type of observations. Now, to conclude my part, I'm going to talk about, we want to really look at long-term trends. That's what we're really concerned with. And in order to be enabled to do that, we need observations that span that entire period of time. And a challenge in doing that is lifetime of instruments, right? And typically, as I said, the instruments typically last something like 5-6 years. They're designed for that period of time. It's just fortunate that we've been, for extremely good, wise design decisions, we have instruments that have way outlasted their design lifetime. So you have the TRIM instrument that failed in 2000. It was launched in 97. We have Terra, which was in 99, and it had a design lifetime out to 2004 or 2005, but it's still operating right now. Aqua, the same. It was supposed to last till 2007, but we're still operating. FM5 and FM6 on SUMI and PP and NOAA 20 are still operational as well. And the next instrument is Libra, which was awarded competitively to LASP, which is a part of the University of Colorado, and they're developing this instrument. But we're looking at innovative ways in order to make these measurements looking into the future. As I said, all these series instruments are identical, and they all have the design that was from the 90s. There's nothing wrong with the design, but we're looking at what are more innovative ways of making the same observations more efficiently. So this shows the evolution, sort of all the observations made by series. We have ERB starting in '84 out to CERES in 2017, the last one launched. We have a demonstrator of a new technology, which is going to be enabled by a project called Athena, which was from Langley next year. And Anum will talk about that briefly. I mentioned Libra, which is, again, going to be on one of these flagship missions. And we're looking at this next generation type instrumentation that typically will not go on these big flagship missions like Demeter. And Anum will cover that. So that sort of concludes my part of the talk. Anum, are you on?
Yes, I'm here.
Okay, I will cycle through the charts and please tell me when to move.
Okay, so next slide, please.
Sure.
I apologize if there's background noise. I have my 2 kids here with me because I'm working from home. So if it gets too noisy, I'll tag Mohan in and he can finish the talk. So hold on just a second. All right, next slide, please. All right, so I won't get into too much of the introduction because you guys already introduced me and did a great job, but I'll say this much. So my name is Anum Ashraf. I am the principal investigator for Demeter, and my job at Langley is to lead the Demeter team to develop the next generation of Earth radiation budget observational platforms to measure the ERB fundamental climate data record. And as Mohan did a great job explaining, hold on just a second, guys. Okay, I'm back. Sorry about that. So Mohan gave you a really good introduction about the series and the legacy of that measurement. My job at Langley is to lead that measurement into the future, into the next generation. And I'll be talking about exactly how we do that with this Demeter mission. Next slide, please. So let's talk about the acronym. Demeter stands for Demonstrating the Emerging Technology for Measuring the Earth's Radiation. And it is hosted on a cellular configurable conformable architecture, which is very different from what Mohan just got done talking. CERES is hosted on these large observatories, large flagship missions. And as NASA is moving forward into the next generation, we're trying to get away from those dependencies, those large observatories, and move the measurement forward in a more sustainable, robustness way, and also in a more cost-effective way. So the primary goal of this mission is to continue the long-term sustained and accurate climate observation that's currently provided by CERES. And just to, I guess, reiterate, CERES measured the reflected solar and outgoing long-wave radiation, and Demeter will also measure the same measurements. So again, the current approach relies on flying as hosted payloads. So we are moving away from being a hosted payload, and Demeter is moving the ERB observation forward with an innovative, low cost and risk approach. Next slide, please. So I think Mohan showed a similar slide. I just want to re-emphasize. So this is the evolution of ERB instruments. Well, it's not actually just Langley because there's an instrument on here that's more than just Langley. But
So maybe I can, I don't know if she's having difficulties there, but I can continue.
I am so
there you
sorry. I don't know why my microphone just keeps going on mute.
Oh, okay.
Maybe it's a good thing because my babies are crying in the background. So what I was speaking on this slide while I was on mute was I wanted to emphasize the payload mass and the spacecraft mass of Ceres versus the payload mass and the spacecraft mass of Demeter. And as you can see, there is a large difference where Ceres is hosted on large observatories that are close to 2,500 kilograms, whereas Demeter, the entire spacecraft, including the payload, is about 100 kilograms. So that's how we're moving this more cost-effective, innovative solution into the future. So next slide, please. So it's not just about replacing a Ceres instrument, it's also having this implementation strategy and strategically evolving Earth radiation budget into the next several decades. We have an opportunity to really go back and survey our key stakeholders, which includes, scientific community, our data users, people who use our products, and just, the mankind in general, what is really needed. And then based on that survey, we prioritize our needs. What is really needed? We need to continue the robustness. We need to improve the science. We also need to reduce the cost as we're moving this into the next generation. We want to reduce complexity and have a higher spatial resolution. I'll get into how we do that, but these are sort of the needs that we sort of gathered from our stakeholders. And based on those needs, we defined our future concepts, and that's defining the architecture, or what architecture will take this measurement into the future. And then we identified different gaps, whether those are technology gaps, demonstration of technology, or just knowledge base of the team. And then we talked about, how can we reduce those gaps? And that could be anywhere from identifying common needs of our partners and opportunities for collaborations, or just developing or maturing our TRL and opportunities we can sort of define in maturing our TRL. And then we deliver on those opportunities. So today I'll briefly talk about the Athena project, which is basically a technology demonstration. Mature the architecture that Demeter will be flying on. And I'll talk about the architecture and then I'll talk about the IIP project. That's where we are advancing the broadband sensor, which will measure the reflected solar and outgoing long-wave radiation from the top of the atmosphere. So there's two different efforts that I'll sort of touch on, and that goes along the lines of how we're advancing the architecture and then also the sensor into the future. So just to kind of, realign where we started. So this actually effort started back in 2018 with very little CIF money, and I think CIF stands for
Center Innovation Fund.
Yeah. So it was like a very small chunk of money that they provided to the team and asked, what is an innovative concept that you guys can come up with that would advance the next generation? And I'm happy to report that over the last several years, we have currently secured $17 million in funding through 2024 that advances this concept into the next generation. So that's a big progress for us. Next slide. So Mohan showed this science traceability matrix for the Ceres instruments. What I'm showing here is how we're advancing this into the next generation. So this is a Demeter science traceability matrix. And everything you see circled in red is what's sort of changing from the current measurement. So that includes increased spatial resolution. Mohan mentioned that Ceres footprint is about 25 kilometers on the ground. So we are increasing that spatial resolution by having a smaller footprint on the ground. We want to sample every quarter by quarter degree grid box on the Earth. And then there's other things that you can see on the slide that we're advancing. But the main point on this is that this traceability matrix is a consequence, I guess, of several different instruments and several different measurements that fuse together to bring this Earth radiation budget data together. And as Mohan mentioned in his presentation, that you have this observatory, you've got the CERES instrument, and then you've got MODIS, and then we use the geostationaries, and that's what brings all the data together. So there's a lot of external dependencies. And with this Demeter effort, as we're going into the future, we'd like to get rid of those external dependencies. So the concept is that the single ERB sensor craft, the architecture, will carry the broadband sensor and the spectral radiance sensor. And the way you satisfy the diurnal coverage is you fly these in a constellation. So you have multiple sensor crafts and multiple orbits providing you that global coverage. So this way you're not dependent on first large observatories and then also geostationaries. So this way you are more robust as you're moving forward into the next generation of making these measurements. Next slide, please. Okay, so then I will talk about you'll hear me say IIP, which stands for the Instrument Incubator Program. And that's where we are advancing the broadband piece of this science traceability matrix. So the current focus is maturing the TRL of the broadband sensor. And that includes maturing the architecture through the Athena Technology Demonstration Program and then also the IIP program. So next slide, please.
Just to clarify, TRL stands for Technology Readiness Level. It is just how mature the instrument is for flight.
Thank you, Mohan. We speak about acronyms all the time at NASA. Sometimes I forget to define them, so I apologize. Next slide, please. All right, so this is the product breakdown structure. I know it's a lot of information, but let me just break it down a little bit for you so you understand what parts are we advancing with the Demeter concept and what parts are the significant contribution by the Athena project. So everything you see circled in, I guess that's a pink or reddish color, is what Athena is bringing to this sort of ERB mission. Again, Athena is a technology demonstration unit, and basically what it is, it takes the CERES, the original CERES telescope module, and it's hosted on a architecture that we're trying to advance and use for the Demeter mission as well. So it's hosted on that sensor craft, and it will be flying in the respective orbit. And it's basically going to prove the proof of concept of that architecture. And everything you see on pink is the significant contribution by the Athena mission. And then everything you see in yellow is what's the focus of the Instrument Incubator Program. So again, we're focusing on the broadband sensor, and then the broadband sensor further is broken down into several modules. That includes the optical, that includes advancing the optical module, the calibration module, and then each of those modules are further broken down into their sub-assemblies. And I won't go into too much detail, but you can see there's different things that are associated with the different modules. For example, telescope, advancing the filters and the detectors and things like that. So next slide, please. So this is the concept of operation. So Mohan, if you can hit play, but mute the video. Yep. Great. All right. So as I'm talking, you guys can see the architecture on the bottom left-hand side. And Mohan, you may need to play it more than once, but basically it shows you how this architecture, these Lego-like structures come together to form the complete sort of, as you can say, bus that hosts the payload. The picture on the top right-hand side shows the comparison of these architecture, and it's just enlarged for comparison. But as you saw in a previous chart, I compared the size. Demeter is a lot smaller than the traditional CERES hosted on the observatories. But going back to the concept of operation, it is a non-scanning wide field of view radiometer that measures limb-to-limb TO irradiances while integrated with the NovaWorks hyper-integrated satellites. So these little cubes that you see in the video there, those are called HiSats, and you'll see me referring to them in a future slide as well. So the picture on the right also shows that both CERES and Demeter are measuring the same limb-to-limb measurement. However, CERES scans, whereas Demeter is a more push broom approach. And the push broom approach is what makes Demeter a lower risk and a lower cost option. So the detector in the Demeter is oriented perpendicular to the satellite ground track. So it's collecting as it's simultaneously moving in the orbit, and it collects a single limb-to-limb swath based on the technology of the detector. The picture on the bottom next to the video is a conceptual drawing of what Demeter could look like. It's very similar to what actually Athena looks like. But basically the concept is you have these rectangular or these square boxes that sort of come together in a Lego-like fashion, and then they can host the broadband sensor or the imager or whatever your instrument is on its platform to provide you your measurement of interest. So there is just a conceptual drawing that's hosting the Demeter payload, and then you've got telescopes on the bottom, and then you've also got some calibration sources. Next slide, please. All right, so this is the HiSats that I was speaking about. These are the rectangular boxes that you saw in the previous video. So these are actually connected to aggregate performance as package of aggregated cells. And on the left, I won't go over all the characteristics, but basically, it provides all the necessary capabilities that's needed for an autonomous satellite. And there's advantages to going this route, but all of the specs, all of the, I guess, advantages are listed on the left. There's high performance bus can be built in months, not years. So that that allows you to build these instruments and conform to these architecture a lot faster than your traditional observatories. Supports all orbit. We're actually going to show that with the Athena demonstration as well. It's more payload centric. So what that means is you bring the payload to the HiSats, and the HiSats sort of configure themselves around your instrument. And it's just, they share resources, all of the different boxes that you see, the Lego-like structures, they share resources. So there's a lot of redundancy. So if one was to break down in some aspect, you can sort of share the resources among the other HiSats to sort of compensate for if there's any, failures on orbit. So that's that. And the measurement over there, it's written, it's a 20 by 20 by 10 centimeters. So it's not a huge, cube. It's a small cube. And you can use as many as you want, depending on your mission. And that's all I'll say about that. So next slide, please. All right, so let's talk a little bit about the specifics of the instrument incubator program. The goal for this program is to advance the broadband sensor, as I showed you guys on the science traceability matrix. That's our first goal. So just to, I guess, realign, IIP is part of an overarching effort to strategically evolve the ERB measurement into the next several decades. And we started with the Athena project, which is, I believe, is to launch next year. And then we're transitioning from Athena to IIP, and then hopefully from IIP to a full Demeter constellation to get us all the data products that I showed you on the science traceability matrix. So IIP addresses the technology gap of the broadband sensor, and it was awarded by Earth Science Technology Office at NASA. And we kicked this project off in January of 2020, and it's a 3-year effort. It advances the technology readiness level from a 2 to a 4+. And basically what that means is that we'll develop a laboratory prototype as a follow-on transition to a low-risk flight mission. We'll also carry out studies about the calibration module, because the calibrating this instrument is just as important. And then we'll also have studies on the modular architecture, the HiSat architecture, and how that architecture sort of could come together to host this broadband sensor and the calibration module. We have an excellent team from Langley's previous ERB science groups. So we've got all the experts providing us insight as we're advancing this concept into the next generation. And then we have a lot of internal and external partnerships, and that's within NASA, industry, and also academia. So we've got a great team, a large group of people who really have worked on the series instruments for the past 20, 30 years, and we're taking that knowledge and bringing that with us into the next generation. Next slide, please. All right, so I'll just quickly go over this. I wanted to include this slide because it shows you the amount of work that went into advancing this concept. So this is a design summary. There's a lot of inputs that go into when you're developing these instruments. The inputs like, how would we calibrate this instrument? What are the precision and accuracy requirements? What are the performance requirements? And most important, how much will it cost? So again, this is a continuity effort. So we want to make sure we carry, okay, hold on just a second. So we want to make sure we carry the same precision and accuracy into the next generation. And then there's several design trades and studies that we performed with this design as we mature them. Some of those aspects include looking at sensitivity or polarization. How many mirrors can we afford? What are the available technologies in respect to detector? The different type of mirrors and how we would calibrate it. Hold on. And then based on those design trades and studies, we arrived at a concept which includes a single mirror design, a freeform optic, a planar detector, and a tiled approach to get the complete full field of regard of 120 degrees. The picture on the bottom left just shows a ray trace of, I won't go into too much details about the design because it is competition sensitive, but just to give you a feel for the ray trace, you have a single mirror and how that arrives at your focal plane module. And then you have a 3D CAD drawing on the top as well, just showing you, orienting you how your freeform optics, sort of how you ray trace in a freeform optic and how the rays arrive at your detector there. So next slide, please. Oh, I think that's it. So this is actually a video that'll probably be.
So
go ahead, Mohan.
So I had sent you a link. So would you mind?
Request.
Yes, sir.
Yeah, sure, sir. We'll be sharing it for you. Yeah, sure, sir.
Shall I stop presenting then?
Yes, sir, please.
Okay.
Requesting one from IEEE PMSB to please share the video.
Using an innovative and integrated approach, NASA's Demeter mission demonstrates the emerging technology that measures the Earth's radiation budget from the top of the Earth's atmosphere. Demeter preserves the existing ERB data continuity while increasing capability with a solution that reduces cost, size, mass, and overall risks associated with data gaps. Demeter ERB sensor craft will fly as a constellation of small sensor craft in multiple low Earth orbit planes. Current constellations contain 9 significantly larger observatories that are distributed in low Earth and geostationary orbits. Demeter reduces the mass on orbit by a factor of nearly 70. The radiation budget for the Earth is a balance between the energy it receives from the Sun and the energy it radiates back into space. Demeter will measure the total broadband radiation leaving the Earth's atmosphere system, which includes reflected solar and emitted thermal or outgoing long-wave radiation. A delicate balance of incoming and outgoing energy makes our planet conducive to sustaining life. Continuous measurement of this balance is fundamental to enabling humanity to adapt to a changing world for generations to come. Demeter's wide field-of-view push-broom observation approach will produce calibrated data that is accurate and stable for climate monitoring, while significantly increasing spatial resolution compared to its predecessor instruments. Demeter will also incorporate intelligent onboard data processing capability that allows for rapid data distribution to the science community, such as the CERES Flash Flux product stream, to support scientific field campaigns, enable educational data exchanges, monitor solar power production and building energy efficiency, and provide data for in-growing season agricultural modeling. Demeter's drastically reduced form factor using NovaWorks' cellular configurable architecture enables low-cost flight opportunities, which significantly reduces the risk of a gap in the multi-decadal climate data record and also facilitates future technology infusion. The Demeter team capitalizes on more than 40 years of Earth's radiation budget measurement knowledge and strategy at NASA's Langley Research Center. Demeter could tentatively take flight in 2028.
So with that, that concludes our presentation. Thank you for your attention, and we'll be happy to take questions if anyone has any.
Thank you, sir and ma'am, for an enlightening and knowledgeable presentation on clouds and Earth's radiant energy system. We are privileged enough to have witnessed such an amazing session just via our computer screens. Now, moving further, I would like to invite the moderators of the session to ask the questions to experts.
So the first question is, what are the major implications that would be considered in the measurements of Earth's energy budget?
Could you repeat that again, please? I'm sorry, you broke up for a second.
Okay. What are the major implications that can be considered in the measurements of Earth's energy budget?
Okay, so I covered that in the earlier part of the talk, where the needs for these measurements include things like what type of time scales that we have to make these measurements over, what type of spatial scales we have to make those measurements over, and indirectly what type of spectral ranges do we have to cover, and angular coverage and things like that. So in the design of a system like this, you have to factor in what are the types of effects that you're trying to measure, and you have to factor in things like the Earth's natural variability, and what timescales those are over. Things like the El Niños and the La Niñas, right? They cause temporary changes to the Earth system, to the temperature of the surface, but they're not long-term changes. And so if you're trying to monitor these really long-term changes, we have to have instruments that span multiple decades. In the design of that, you got to factor in how long each of those instruments can last, and ensure that you make continuous measurements past the lifetime of each of those instruments. So there are a lot of all these factors that come in when you're trying to design a measurement system like this. And it's a very complex process, which also includes things like what the climate community needs. What measurements do they need to enable to improve their models, etc. So there are a lot of these complex factors that are brought in when designing such a system to measure the Earth's radiation budget.
So the next question is from Harsh. Assuming that the series data can be used for assessing radiative effects and climatic impact on Earth, is it possible to prevent or predict upcoming natural disasters like volcanic eruptions, drought, etc.?
I mean, all we can enable with the observations from instruments like CERES are effects on the Earth's atmosphere and indirectly the surface. What this enables are not necessarily things like predicting volcanoes and when they might erupt, but we get a sense measurements of what to expect in the future when it comes to things like oceanic and atmospheric circulations. It could be more hurricanes, cyclones, and such. It could affect, monsoons, the rains, and the magnitude of those monsoons, and the impacts due to floods, or things like, global sea level rise. Those are the type of things that these measurements enable, more so because we have observations over such a long period of time. So that way, if you have those those temporary heat waves or those cold snaps, you're not thinking that those effects are because of climate change. Those could just be, those occurrences might be more frequent, but they're not directly as a result of climate change, just because it's colder one day. So to answer the question, it really, you can prepare for the future based on the data that you have. You may not be able to predict exactly when all these events might occur.
So the next question is from Ibrahim. Considering normal and artificial phenomena happening, which can be considered as some impacts on the Earth's energy budget?
I'm sorry, I didn't understand the question. Can you please repeat that?
So considering normal and artificial phenomena happening, which can be considered as some of the impacts on the Earth's energy budget?
So I don't fully understand what artificial effects are. There are the natural effects, which are things that you really don't have control over, changes that might happen um, due to the sun, things like volcanic eruptions that are all within the Earth, and those are not necessarily driven by human activity, but what really, as we are learning more and more in looking at these data sets, what we're learning are that changes are occurring in the Earth, and they're not necessarily driven by the natural variability. So we have to combine observations from not just series, but we have to look at it from a holistic way, including other observations that might be telling, making more direct measurements of um, carbon dioxide in the atmosphere or aerosols and things like that, and incorporate all of those observations to get a global view of what is actually going on. I hope I answered that question. I'm not sure exactly where that was coming from.
Yes, sir. So the next question is from Harsh. From the solar spectrum, can series data predict a threshold value of thermal radiation of Earth that can potentially reach the temperature of neutron stars' active galactic nucleus?
I don't think the series observations would be able to predict that. All we can do is, again, we're only enabling climate modelers. We're not actually even predicting the temperature of the Earth. All we're saying is, this is what the observations are, and this is what the trend, this is how it has changed over time. And this is how it has changed over spatial scales in different parts of the globe. And we can just get those snapshots at all these different scales of either time or space. So it doesn't necessarily relate to what might be happening outside of the Earth.
So the next question is from Harsh. Can data-driven astronomy enable us to measure the concentration of dark matter around Earth or empty space someday?
That's outside of my expertise. So I apologize. I wouldn't be able to speak to that. All I can say to that is, so the exploration of dark matter is a lot of people are working on that. I am not one of those. We are focused more on Earth science and Earth observations, remote sensing of the Earth from space. So I would defer to someone who might be an expert in dark matter and those topics.
Sir, I think the time is exceeding too much. So I think, would you be able to take more questions or would we email it to you afterwards?
I'd be happy to answer over email later.
Yeah, that would be okay. I request all the participants that we would be sending all your questions to sir through emails, and we will be sending back to the emails whatever sir would give the answer. Now I request host to please continue further.
Thank you, sir. Continuing further, I would like to invite Dhruv Pokar, Secretary NPSS Chapter and Senior R&D Officer, IEEE BVM SB, to deliver the vote of thanks.
Thanks. I would like to thank Dr. Mohan Shankar sir and Dr. Anum Ashraf ma'am, for delivering such an insightful and wonderful session on the Clouds and Earth Radiant Energy System series, the only project worldwide responsible for producing the climate data records of ERB. Further, I would like to thank Dr. Indrajit Patel, sir, Principal, BVM Engineering College, Dr. Jagdish Rathore, sir, Faculty Advisor, IEEE BVM, and Dr. Darshan Dalwadi, sir, Branch Counselor, IEEE BVM, for their guidance and support in organizing this event. Also, I would like to thank Dr. Reses Mehta, sir, for the warm introduction of our expert, Nitya Parikh, host of the session, and all the moderators of the session. Also, a big thanks to our organizing team and the entire IEEE BVM team to plan and conduct such a wonderful event. Thank you. Have a great evening. Thank you.
Thank you, Dhruv. It would be kind enough of you, sir and ma'am, to keep the camera on so we can take a screenshot for the report. Mohan, sir? And
Yeah, I
ma'am?
can certainly do that. I am not sure if Anum is
Yeah,
around.
no
I think.
issues. No issues.
No
Only
issues,
if it's possible. No issues. Ma'am.
Sure.
I also request the team members if they can turn on the cameras. Question someone to please take one screenshot and let us know once it's done.
It's done.
Thank you, sir.
Thank you very much for the opportunity to speak to you all.
Thank you, sir.
Yeah, I wish you the best with everything, and please, if you have any questions, please send them to me. I'll be happy to answer.
Definitely, sure, sir. Thank you so much for such an amazing session.
Yes, sir. So the trial questions were answered perfectly.
Oh, great. I tried my best.
Yes, sir.
Thank you, sir. Thank you so much, sir.
All right. Thank you very much. Have a good evening.
Thank you, sir.
Goodbye.
Goodbye, sir.
Goodbye, sir.
Now, I would like to invite Dr. Jagdish Rathore, sir, Faculty Advisor, IEEE BVM SB, to give an overview of the International Colloquium on Emerging Technologies 2021.
Yes, thank you, Nitya. Am I audible?
Yes, sir, you're
Hello.
purely audible.
Thank you very much. Thank you very much. And first of all, I must congratulate the student team because this has happened because of your efforts. Yes, this is another event done by our IEEE SP, and that is very nicely organized. And this International Colloquium on Emerging Technology 2021. There were 7 sessions, 7 speakers, and 5 days, starting from 18 to 22nd September, means today. And I'm witness of these speakers, like for the Industry 5, topic was Industry 5.0, Mr. Pratik Gauri, then Internet of Behavior by Ms. Rajeshri Rao, then Blockchain and Self-Sovereign Identity by Ms. Carolina, Digital Forensic by Mr. Deepak Kumar, then Computer Vision and its application by Sai Harish, and today's sessions by Dr. Mohan Shankar. So, and I wish to share some other information, and that is I'm thankful to my team who has shared me, that I wish to inform to all that registration was 1,500 plus, views were 6,000 plus, countries participated were 8 countries. So I'm thankful to you all, and it was a nice success. Thank you very much. I wish you all the best for future events. Thank you.
Thank you so much, sir. Moving further, I would like to invite Om Shukla, Joint Secretary IEEE BVM SB, to give the preparation overview of ICET 2021.
Thank you so much, Nitya. Good evening, everyone. Empowering Technophiles, Envisioning Tomorrow, the aim with which we started this mega event, the International Colloquium on Emerging Technologies 2021, has been achieved on a large scale with the experts empowering our technophiles to envision their tomorrow with the most emerging and vibrant technologies of the future. Our team began the preparation of the event from 1st of August 2021, and almost 2 months long dedicated hard work of Team ICET 21 has resulted in the successful completion of this grand mega event without any hustle, panic, and delay during the entire duration of ICET 21. The team was so dedicated that it was working even during our mid-semester examinations, which was taken in mid of August. Working late at nights, even sometimes till 2 a.m., has made us reach where we stand today. At this moment, I would like to thank Dr. Indrijit Patel, sir, Principal, Birla Vishwakarma Mahavidyalaya, for allowing and supporting us in the conduction of such grand events. I would also like to express my gratitude towards Dr. Jagdish Ram Rathod, sir, Faculty Advisor, IEEE BVMSB, and Dr. Darshan Dalwadi, sir, Branch Counselor, IEEE BVMSB, for their constant support and motivation. Let me also take this opportunity to mention our most cooperative and helpful mentors of Executive Committee, Mr. Jamin Shimpi, Mr. Ibrahim Koicha, Mr. Jailraj Singh Mahida, Mr. Galo Bhatt, Mr. Gaurav Barve, Mr. Dhruv Kokar, Mr. Atharu Bhave, Mr. Khanjan Marthak, Ms. Venu Padhyay, Ms. Pankti Shah, and Mr. Jay Prajapati. A big thanks to each and every one of you for being available 24/7 to help and guide us in each and every small stuff. At last, let me mention the heart and soul of this event, the organizing team of ICET 21. I would like to mention the other two leads along me, Mr. Shailesh Bamania and Mr. Kevalya Pandya, and the members of organizing team, Ms. Nitya Parikh, Ms. Devanshi Suthar, Ms. Hemangini Bhatt, Mr. Rishit Thakkar, Mr. Swar Shah, Mr. Hit Patel, and Mr. Yash Tibra. Thanks to all of you for such an amazing, dedicated work resulting in the success of the event. Also, thanks to Mr. Swar Shah and Mr. Rishit Thakkar, our YouTube coordinators, for taking this event live on YouTube for our participants. Thanks to all the hosts and moderators. Also, big thanks to all those who were directly or indirectly involved in the success of the event. Hoping to organize such more grand events under the banner of IEEE BVMSB and continuing the legacy. Thank you, everyone.
Thank you, Om. Now I would like to call upon Dr. Darshan Dalwadi, sir, Branch Councillor IEEE BVM SB, to give valedictory remarks.
Good evening to all. On behalf of IEEE BVM Engineering College Student Branch, I want to thank all the experts, starting from Mr. Pratik Gauri, President, United States-based Fifth Element Group, Ms. Carolina Gorna, President, Cryptosphere at France, Ms. Rajasri Rao, Head of Artificial Intelligence, Innovations Hub and Partnership and Ecosystem at R-Squared Data Labs, Rolls-Royce. Mr. Deepak Kumar, a Senior Digital Forensic and Cyber Intelligence Expert. Dr. Sai Haris, Research Expert at SAP Innovation Center. Dr. Mohan Shankar, Science Directorate, NASA Langley Research Center. Dr. Anum Ashraf, Principal Investigator, Demeter, IIP at NASA. I thank you very much to all the experts. Further, I want also thank Engineer Bhikubhai Patel, sir, Chairman Charuta Vidya Mandal and entire Charuta Vidya Mandal team for providing all kind of support. I would also thank Dr. Indrajit Patel, sir, Principal BVM and President of the ICET. Thank you very much, sir, for always the motivations. I would also thank Dr. J.M. Rathod, sir, convener of the ICET. I would also thank Professor Mayur Sevak for press and media support. I would also thank all the department heads and faculty members of BVM Engineering College. I would also thank Dr. Kausika Patel, ma'am, Dean, International Collaboration Cell of BVM Engineering College, and particularly our international academic partners, University, Ural Federer, St. Cloud State University, Illinois Institute of Technology, Laurentian University, and many more. I would also thank Gujarat Technological University and CVM University for support. I would also thank all the participants. I further thank our student organizing lead committee of ICT, particularly Om, Silas, and Kavalli as the lead member. I would also thank ICT team members, Devanti, Nitya, Swar, Heath, Risit, Hemangini, Yes. I would also thank our executive committee members, Jamin, Simpi, Chairperson, Ibrahim, Vice Chairperson, Galav, Secretary, Dilraj, Treasurer, Venu, Public Relation Officer, Kanjan, Webmaster, Gaurav, Chairperson, IEEE NPSS, Dhruv, Secretary, IEEE NPSS, Atharva, Marketing Lead, Pankti, Publicity Head, Jay Prajapati, Senior R&D Officer, Isan. Thank you very much to all.
Thank you so much, sir. On behalf of Team ICET, and the entire IEEE BBM student branch, I would like to thank each and every one of you for joining today's session. Hope you all have learned much to fulfill your vision, empowering technophiles and visioning tomorrow. Thank you.
See you. Bye.
Thank you, sir. Requesting to please stop the live and as well as the recording.